will tell us whether deeper is better only when shallow is good.
Thank you, Ahad, and thank you for inviting me. So this is basically a work by my student, Eran Malach, who's sitting here. So as a motivation, this is coming from a blog by Joel Grass. Probably many of you already saw it, so, but let me, in any case, say it again because it's funny, I think. So it's like a fake interviewer that asks someone to print the numbers from 1 to 100, except that if the number is divisible by 3, print fizz. If it's divisible by 5, print buzz. And if it's divisible by 15, print fizz buzz. So it's a question in an interview. And then the guy say, yeah, sure, I know how to do it. Import TensorFlow, and let's try to build a network for it. And it goes on. I urge you to go and read it because it's funny. I think, at least I think it's funny. At the end, he says, I didn't get the job, so I tried actually running this, and it turned out it got some of the outputs wrong. Thank you very much, machine learning. And I think this is a true story about machine learning. It got some of the outputs wrong in general. And then he ends with, I guess maybe I should have used a deeper network. All right, so a basic question, and this is what I'm going to talk about in this talk, is depth efficiency. The basic question: on which distributions deeper networks are much better than shallow ones? All right, and there has been a lot of research on this question, and there is several examples of depth separation, basically saying that there exist some functions which can be expressed by a small deep network, and small meaning that the number of neurons in the network is, say, polynomially large and not exponentially large, but must have an exponential width in order to be expressed by a shallow network. And this means that we need to go deeper in order to have an overall polynomial size for the network. And there is results by Matus and Ohad and some others that wrote many such results. And what I'm going to show in this talk, or I will try to argue in this talk, is that if there is a strong depth separation, and I will explain exactly what do I mean by strong depth separation, but if indeed you must have exponential size for a shallow network and only small size for a deeper network, then gradient-based algorithm will fail on the deep network. Okay? So in other words, such strong separation between shallow and deep networks mean that it is not a very useful example because gradient-based algorithms will not be able to successfully train a deep network on the problem. And in order to show this, we'll talk about fractal distributions. Fractals are very convenient for studying deep networks because they have many similarities to what's going on in deep networks. So I will show that some fractal distributions can be expressed by a deep network, by a small deep network, but cannot be expressed by a small shallow network. So there is depth separation. And they will allow us to define a notion of approximation curve, meaning how much depth is really needed in order to solve the problem. So we can ask about how good a deeper and deeper network expresses the problem. And strong depth separation means that there is the approximation curve looks like flat, and then at the end it goes up. Okay? And then I will show that success of gradient-based algorithm depends on the shape of the approximation curve, and if there is strong depth separation, then these algorithms are likely to fail. Okay. So I will show it on one example, but there is a bigger conjecture here, and this is only a conjecture, that this is not just for the examples that I will show, but this is actually what happens everywhere in deep learning. So in order to enjoy a deeper network when you use gradient-based algorithms, shallow networks will work as well. Okay? And then at the end, maybe we'll talk about, so why do we need deeper networks? Yeah.
What do you mean by it will work? Like,
it will work means that you can train a shallow network, and you will find a solution which is not random, which is better than a random guess if it's a classification problem.
You can efficiently train a shallow network like that?
Well, if it is very, very shallow, yes, but otherwise, no. Well, we do not have any strong results on efficiency of training. But maybe I will say some words at the end that this is another type of conjecture, that if the approximation curve is nice and if shallow gives you something, then maybe you can even train efficiently in terms of computational power. You can maybe train efficiently deeper networks. Okay, but this is another topic that I will maybe say a few words at the end, but it's not the topic of the All right. So my running example will be fractals. So an IFS, or iterated function system, is defined as follows. We start with a cube, the d-dimensional cube, -1 to 1, the interval to the power of d. This is k0. This will be the first set. So it is depicted here in 2 dimensions. And then there are R functions, f1 to fr. And we apply each one of them on the set. So for example, in the example here, f1 takes the rectangle here and project it here. Okay, and f2 project here, f3 here, and f4 here. Okay, so we apply f1 to fr on the previous set in the fractal, and then we repeat it again and again. Okay, so this gives us a set. The set at the end, after 3 iterations, the set is all of these small rectangles. Okay. We make some assumptions on the functions, that they are affine function, invertible, contractive, and their images are disjoint. This is very convenient for the analysis. The depth of the fractal is n, is how many times you repeat this operation. And the example here is for the function, the 4 function that just squeeze the initial rectangle to the corners. Okay? So this is an iterated function system. Now, what is a fractal distribution? A fractal distribution is a distribution in which positive examples are sampled from the fractal set Kn, and negative examples are sampled from its complement. So if we go back to the example here, so positive examples are from here, and negative examples are from all the white areas, or all the rest. And here are some additional fractal sets, a Cantor set, Sierpinski rectangle, and some more examples. Okay? So these will be our running examples, these fractal distributions. Okay, so what I'm going to show at the beginning is that these are very, very convenient structures for showing depth separation, for showing that you need to go deeper in order to express some fractal distribution. So the first theorem tells you the following. If we take an iterative fractal system in d dimensions, and there are R generating functions in depth n. So the parameters are d, the dimension, R, the number of functions that generates a fractal, and n is the number of times we repeat the process, the depth of the fractal. Now we define any fractal distribution Dn over this set. So for any such fractal distribution, there exists a ReLU feed-forward network of depths 2n plus 1 and widths 5d times r, which realizes Dn completely, exactly. So you can express a fractal distribution with a deep network, and the depth of the network is order of the depth of the fractal.
Realizes means specifies the support of the distribution.
Yeah, meaning that you can get 0 error.
So there is a threshold function at the end.
It's a threshold function. I didn't see who asked. Yeah.
Shai.
Yeah. So just a second. So there is it's a threshold function, but all this works also if you require separation with margin. So you can have margin, and there are no examples in the margin between the difference between the negative and positive areas.
So it sounds from the description that there's only one function.
So say it again.
Given the parameters d, r, and n, there is a single function that classifies the positive to negative. It's not a family of functions. It sounds like a single function.
So first, if you you need also to specify the function f1 to fr. So it's a family of functions.
For every f1 to f.
Yes. Okay. So I'm going to show the proof, and the reason I'm going to show the proof is because it's very simple, and I want to show that fractals are very convenient structures for studying depth separation. So let's see the proof. The proof is by induction, which makes a lot of sense. The basis is to show that a shallow ReLU network can approximate the indicator function for k0, and k0 is simply -1 to 1 to the power of d. Okay, and this is really easy because ReLU function can approximate a step function. So you need the step function for every dimension, and then sum them up, and you are done. Okay. Okay, so now the induction step. Suppose that we already have a deep network that expresses the set kn minus 1. So it tells us 1 if we are on the set and 0 otherwise. Now we recall that the next set, kn, is a union of the application of the r functions f1 to fr on the previous set. Okay? And fi, we assume that there are affine functions, invertible, and have disjoint images. Okay, so what does it mean? It means that if we take now some vector x in kn in the set that we want, now we want to construct I of n, which will be 1 if x is in kn. So if we want to construct such a function, we take x in kn, then there must be some z in kn minus 1 and some index I such that x is the application of fi on z. Okay? But since fi is affine and invertible, we can write it as z equals to fi to the minus 1 applied on x. Okay? So just taking the difference between two ReLUs, we get a step function. Now what we have here is summing over everything in the image of the inverse of f, okay? And this is an affine operation because it's sum. Fine, we can express sum with a ReLU feed-forward function. fi minus 1x is just an affine transformation. So again, we can express this with a neural network. And in minus 1 is the previous network that we had. So we just make it deeper, and now we are fine. So by doing affine transformation and ReLU, we can now express the indicator function for the next set, and we are done with the inductive proof. Okay? So this shows that, and if you do some counting, you see that the number of neurons that we need is small. It's basically linear in the product of the dimension and the number of constructing functions.
Where did you use the assumption that the phi's are contractions?
So let's see if here I used it.
I think it's useful.
Yes, because you want to apply it here. Okay, this is in the basis of the induction. So you all the time in the same set. And this is why the induction works. Okay. So this is one side of the depth separation result, that with a deep network you can express the fractal distribution. Now we need to show that with a shallow network, in order to express the function, the fractal, we must use an exponential depth. And here the theorem says that if the distribution has non-zero probability in any area of the fractal, then, say the uniform distribution, then a network of depth t must have a width of at least something like R2n over Td in order to realize the n. It means that you need that t will grow with n. Otherwise, you will need exponential widths. Okay, so you need that the depth will be order of n, and if it is a constant or much smaller than n, then you have exponential growth of the number of the widths of the network in order to express a fractal. So how do we prove this result? This is also a very simple proof. It's basically a counting argument. So on one hand, a network of widths k and depth t has at most ek over d to the power of td linear regions, and this follows from basic VC dimension calculations. On the other hand, in order to realize a fractal distribution, it is not hard to see that there are R to the n linear regions which are separated, so you must have more linear regions that you can express than the ones that you need, and just by comparing the two, you get the result. Okay, so a basic counting argument tells you that in a shallow network you cannot express a fractal.
But the area that complements Kn is exponentially larger than the union of Kns.
No, not
Because of the
necessarily.
refractive method.
Not necessarily. Not necessarily.
Majority of
Because
the space is negative.
we are not talking about the volume, okay?
Understand. But
We're-
under the assumption that you can sample from each Kn, let's assume, so for any non-contrived distribution, it means that you have an area of the positive examples is exponentially smaller compared in n.
In what sense? In the sense of volume? Volume is not an issue here. The issue here is because you put half of the distribution on Kn and half of the distribution on the complement.
So it's a two-button law. Okay.
Okay? So otherwise, if you take uniform over everything, then you are right that just saying zero every time will be fine.
Would be fine.
All right. So we showed that we showed the fractal distribution, and we showed the depth separation result for the fractal distribution, which is nice, but nothing is very new here. It's just a nice way to show yet another example of depth separation, but it's not interesting by itself. The reason it is interesting is because now we can go to the main claim of this work, that if you have strong depth separation, then gradient-based algorithms will fail. So we need one more step, and we need to explain what do we mean by strong depth separation. So now we will talk about approximation curve and strong depth separation. So far we saw that the network of depths order of n can express a depth n fractal. But if you use a shallower network, you require exponential widths to fully realize the distribution. Okay, but maybe it is hard to fully realize the distribution, but it is not hard to realize it to some extent. So for this, we need to define the approximation curve, which tells us how much of the negative examples are on the fine details of the fractal, or basically tells us what is the performance, the accuracy of using a set, an indicator of a set in the early stages of the fractal in order to approximate the function. So we define P of j for an index j to be simply 1 minus the loss, the 0-1 loss, average 0-1 loss of the function, which simply tells us to say positive on examples from kj and negative of examples of outside of kj. Okay? And j is between 1 and the depth of the fractal. So if we take P of n, we will get 1 because this is a definition of a distribution over a fractal. You must say positive inside the kn and negative outside of the kn. If you take P of 0, it means that you just start with saying positive on everything, and we assume that the mass of negative examples is exactly the mass of positive examples, so the error will be 1/2. So P is monotonically increasing from 1/2 to 1. But the question is how it increases from 1/2 to 1. And there are many ways to increase from 1/2 to 1. But one way is to start very, very close to 1/2 and only at the end go to 1. And another way is to gradually grow from 1/2 to 1. And you see the two examples here. So here, negative examples are distributed in many, many places. And here, negative examples are distributed only on the fine details of the fractal. Okay? So the question is, do we put the mass on the fine details of the fractal or also on the coarse details of the fractal? If we put the mass also on the coarse details of the fractal, then the curve grows gradually from 1/2 to 1. If we put all the mass only on the fine details of the fractals, then we begin by 1/2 approximation, which gives us nothing at the beginning, and only at the end we goes up. Okay? So we call this curve the approximation curve of the fractal, and it is a property of the distribution. So you can keep the same fractal in mind, only change the distribution over the negative examples, and get different approximation curves. So now, what we argue is that the approximation curve tells us something about strong depth separation. So what we say is that if we have a depth n distribution with approximation curve p, then roughly the loss of using neural networks of depth t, where t is almost j, order of j, is roughly 1 minus pj. So it is bounded from above by 1 minus pj and from below by something which is very close to 1 minus p of j. So basically, p of j, if you recall, we defined it by one particular function, the indicator function of kj. But this theorem tells you that roughly for every neural network of depth order of j, okay, the performance will be the same as the indicator function. So it will be like the performance of saying indicator of k of j, okay? No matter what network you will choose. So in other words, P determines how well the class of neural networks of depth t and width k approximates the fractal. Okay? So what we get from here? We get from here a strong depth separation. When will we have a strong depth separation? So if P of j will look like here, so it will be close to 1/2 at small values of j. Then the loss will be roughly 1 minus 1/2, which is 1/2, basically random guess, for every neural network of depth t and width k. Okay, so we cannot find a neural network of depth t and width k that does much better than a random guess. Okay? On the other hand, if the curve looks better, then we know that there is a neural network of depths roughly j and small widths that approximates the distribution according to 1 minus pj. So we will do better than a random guess. So if the curve is like this, we have strong depth separation, because with a shallow network, we will not be better than a random guess, but with a deep network, we will be fine. Okay? So now, arguably, the holy grail of depth separation is to show stuff like this. And now we came to the punchline of this work, is that if the approximation curve looks like this and we have strong depth separation, then it's very nice in terms of expressivity, but it is completely useless in terms of what we really gained from the depths, because we will not be able to train the deep network using gradient descent. Okay, so strong depth separation, if we have strong depth separation, then gradient-based algorithms will fail. Okay, so in order to show this, we will focus on one specific example. It's a one-dimensional Cantor fractal with fine distribution. So it is basically depicted here. We start with the interval 0, 1, and then we take 1/3 and 1/3 and a hole in between, and this will be C1, and then we keep doing it repeatedly in order to build the set. And we will put all the negative examples between positive examples, so on the fine details of the distribution. Okay, so what we show that if you take a depth t width k network and try to train it with gradient descent, so training with gradient descent usually starts with initialization of the weights of the network. So let's W be the weights of the network, and suppose we initialize them randomly in the normal way. By the normal way, I mean usually you initialize the weights by something that is proportional to the inner degree of the node that the weights goes into it. Okay? And you take uniform or Gaussian based on how many edges, incoming edges you have to the node. So suppose that you do it like this. And then you take a depth n one-dimensional Cantor fractal and take some j which is not too small, but is strictly smaller than the depth of the fractal. So we need the depth of the fractal in order to express the distribution. Then with probability of at least 1 minus delta, all the elements of the gradient at W are of magnitude which looks like 1/2 minus P of j. Now, if P of j is close to 1/2, it means that when you initialize, all the gradient is basically 0. So you will not make any progress starting to optimize from that point on.
So is J the size of the network, the depth of the network you're training?
Say it again?
Is J the depth of the network we are
D?
training? J.
J. Yeah.
What happens for J greater than n or equal to n?
So this is true for j equals n minus 1. What happens?
So because
What happens with j larger than n? Actually, I don't know. Eran, do you know?
No, it's not that j is just fix any j between this interval.
no, but in this case the network is not realizable, right?
T is the depth of the network.
Oh, T is the depth of the network.
Yeah, I missed it.
Oh, okay.
So j is just any number. So this is true for any j.
So just
It just needs to be larger than log of t. So j is just a number that tells you how the approximation curve look like. So if the approximation curve is flat above log t, which is t is the depth of the network, and k square k is the width over delta. So if this is just a number, okay? So suppose that you want to take the depth to be 10 times n. Okay? N is the depth of the fractal. Okay? So you're saying I want larger than n, 10 times n. So there is a number, and you decide on some width k. I don't know, it will be 100 times d times r. Okay? So you get this number, log tk squared over delta, which grows just logarithmically with the depths that you chose and the widths that you chose. Okay? So you get some number. So if j, now j, you can take it to the integer larger than this. If j is greater than this, and the approximation curve is such that p of j is close to 1/2, then you will not be able to train the depth t network. Okay? Now even I understand it.
So this theorem says that the gradients are small, but why does it mean that?
Well, you are doing gradient descent, and the gradient is almost 0.
So it's just a time complexity is going to be exponential.
Yeah. You will not make any progress in the beginning. Yeah.
To make it formal, you really need Pj to be extremely, extremely close to 1/2. So this
Yes.
is-
It can be.
make
So you can make it equals exactly to 1/2. And then you are at the local minimum at the initialization almost surely.
What are the norms of the weights that realizes this distribution?
Very small. I mean, this now
There
depends.
is a realizable
Yeah.
function with small weights.
Yeah.
It's not that they sort of hinges on the normal initialization.
No.
Okay.
Can you say something about the higher order derivatives?
About the error derivative?
Higher order derivatives like second or third.
I don't think so. I don't think so. Eran, you know, something about the Hessian or? Yeah. But this is just for theoretician Hessian.
No.
Yeah.
The previous theorem had j equals 2n plus 1, I think.
It's just an index. Here it's a different meaning for j.
So it's
So j here is, you can actually think about the theorem as j equals to the smallest integer larger than this quantity.
So I think that an interesting question is here, what properties of those fractals do you need for this negative result? And what properties of the fractal do you need for the separation result? I mean, the fractal is a concrete problem, it is a concrete example. But you probably use some properties of it in order to show this result.
So for the previous results, for the strong depth separation, we just used that the fractal is by affine transformation and contractive, so mild assumptions. This theorem is for a very specific fractal. Okay, it's for the one-dimensional contour distribution. Okay, so it's much weaker than what we had before. But save this question. So this will be the conjecture that what we believe is that this is not a this is what we managed to prove for. But we believe that the theorem is correct for not even for fractals, but for every distribution. Okay.
So this is for the true population gradient, right? You're talking about the
Yes.
initialization point. So can you actually say anything about the stochastic gradient descent itself?
We didn't work on it. I don't know.
I see. In the sense that it will, I guess you will get some kind of random data-dependent walk, and then it's less clear that you will still be in a place where the gradients are small, or?
Yeah, I agree. I mean, basically, Ohad has nice examples of places when the gradient is extremely small, but some miracle happens and you go out of there, right? In PCA, for example. But I think it's a strong evidence that something very bad happens if you try to optimize it. Now,
SGD with adaptive regularizer the norm won't be small.
in general, I think it's worse than gradient descent. All right. So this is just an empirical evaluation where what you see here is that you see different curves, different approximation curves. This is a nice approximation curve, and then it becomes worse and worse and worse until it's completely flattened and goes up. So these curves will be the indices for this graph, okay? And what you see here is what happens to learning depth 5 network on the 2D contour set of depth 5 as a function of how nice is the approximation curve. And as expected, you see that the accuracy, you can reach a very high accuracy if the approximation curve is nice, but as the approximation curve becomes smaller and smaller, the performance goes down. Now, this is just a two-dimensional problem, so you still get better than random. You can actually memorize things here, okay? But in higher dimensions, what we expect to see is that we will go to 1/2 when the approximation curve will not look nicely. So this brings me to the main conjecture that we want to draw from this fractal distribution, is that what happens in deep learning is that it's not a game of you must go deeper and then you succeed, and if you go shallow, then you cannot do nothing. So deep networks going deeper helps you. It really helps you, but only if the situation is not so bad, even with shallow networks. So this is just experiments with CFR10. And if you look at the effect of depths on learning, then you see that as you go deeper and deeper, performance improves, but not that much. It's not a matter of nothing with shallow and 85% with deep. It's even with a very shallow network, you get to 70%, and then you go to 80 and 83, 84, 85, but no, you can get 70% even with a shallow network.
What is the red curve?
This is width and accuracy.
Depth.
The depth is the colors, and you can guess.
What is the shallowest you trained?
The shallowest, wow, I don't know. One layer. Just linear function.
One hidden layer?
One hidden layer.
Oh, one hidden. I see.
Yeah.
But I think the gap does increase if you go to complex tasks with like ImageNet. So this is like,
Yeah, but is it random guess, and isn't nothing with shallow, and is it strong depth separation? Nothing with shallow and
almost like if you have 1,000 facets.
Do linear classifier on ImageNet, you get almost nothing, right?
well, I'm not sure, but even if it's true, then with one hidden layer you get more than nothing. Okay, and there is a paper actually that a recent paper, I don't remember, and it's a pity that I didn't put it on the slide, but that did these experiments with ImageNet and showed that even with a shallow network, and then you do greedy layer by layer training of the network. So even with a relatively shallow network, you get to non-trivial results. Okay. And if it's not the case, then I argue that deep will not help you at all.
Also, like, the relevant quantity for this separation is the loss, right? Not the error. So like for ImageNet, even if you get base field what looks like
Maybe. I mean, if you look,
accuracy, you could still have a significant improvement in the loss compared to a random net.
that's probably true, and this is probably true if you look at the gradient of a nice loss function in terms of success. Yeah, good point. All right, so
Also in your result, like when you showed gradient norm is small, with respect to what loss was it?
it was hinge loss, I think.
What about logistic loss? Same. Distribution.
Okay, so just two last slides to wrap up. So fractal distributions are very natural for studying depth efficiency of deep learning. It is really very simple to prove depth separation for such distribution. We introduced the approximation curve, which quantifies how much going deeper really helps you in terms of expressivity. Strong depth separation means that the approximation curve is flat and only at the end it goes high. And our conjecture is that gradient-based algorithms fail when there is strong depth separation. So in other words, deep is better only when shallow is also good. We didn't prove the theorem. We show it in one very particular case of the one-dimensional contour distribution. So if we want to talk a little bit in more detail about this conjecture and direction for proving the conjecture, so we think something along this line. Let H be all functions which cannot be approximated by a shallow network. Then we think that the following two things are true. First, for each function within f, so again, a function which cannot be approximated by a shallow network, then there is some distribution that depends on f, for which f realizes the distribution. It achieves zero loss, while the best shallow network achieves a loss which is close to 1/2. Okay, so this is one result. That for every function in this class, indeed, there is a need for a deep network, and shallow network will not work. And the second argument is that for every such df, so if you find this distribution for which the best shallow network is close to 1/2, and then gradient descent fails to learn a deep network. Okay? So for this particular distribution. So we think that this is roughly the way to tackle the conjecture, and we urge you to work on this problem. Thank you very much.
So the experiment, if I want to test it experimentally, I mean, after this whole program of deep networks, I realized that what you do is testing experimentally when you don't do theory. So if you want to test experimentally, what you mean is whenever we succeed to learn with deep neural network and we use gradient descent, we should also try shallow network and we'll do it.
Yeah, not as well, but you will not achieve random guess performance.
And I know, like examples in literature of things that people demonstrated that they can solve this problem well with deep neural networks with gradient descent.
To the best of our knowledge, all the successes of deep networks, shallow network, and now we can argue if shallow is one hidden layer or two, but shallow networks achieves non-trivial results.
Seems like I can transform. If I have an arbitrary problem where shallow network can guess, you can imagine like fitting the best shallow network and then like adding it to the logics at the end, such that it's like very hard for shallow network to add value. Is that same right? Or is that some way to test that?
Well, you can do it, but then the question is, will you be able to train the deep network? And I argue that you will not be able to train it.
Is that a reasonable test of that concept? Like I take some deep network, train a shallow network on ImageNet, add the shallow network to the logic, such that it's very hard for shallow network. Now I shouldn't be able to train a deep network either.
What's the fractal dimension of C, for instance? No, it's possible to calculate.
I don't know how you calculate such a thing.
It's a finite data set. It's high dimension. Let's assume that it's a point distribution of that data set. And you take one cluster. So you can ask, what is the depth? What's the minimal fractal number that will shatter the
I can see a way to calculate it, but
you don't have an estimate.
I can't.
Okay, maybe we'll take further questions offline in the interest of time. So we're going to take a break now and resume at 4:15.